much. And indeed, this work, the work I'm going to present, has been done with various people. So the group in Trieste, Naples, and the collaboration with Marco Schirò and Jack Turkeshi in Köln, and as Joanna said, with the group of Anna Maria in Colorado, so Boulder and Cambridge. I will mainly talk about these last papers that we wrote on this topic, something which was already published, and two recent preprints. So I'm going to talk about many-body open systems that have been studied recently in many different platforms, and besides those cases where they correspond to really physical synthetic system, I would refer also to the case in which dynamics in, let's say, in quantum circuits is eventually interdispersed by measurements, intentional or unintentional, due to environment. Roughly speaking, in all these cases, if we are interested in the dynamics at the level of density matrix, a good description is given by Lindblad, in which there is a term determined by the unitary part of the evolution related to the Hamiltonian of the system, or let's say associated with the various quantum gates. And there is also, there will be a term which once we specify the Lindblad operators will describe let's say damping, dissipation, decoherence whatsoever, and many of the phenomena which people are looking in the system arises because of the competition between unitary dynamics governed by the Hamiltonian and the dissipative part associated with this term here. But actually, this is not all, because we can be interested in not only looking at the average dynamics fixed by the density matrix, and actually we might be interested in considering the single process. If we are able to follow, to monitor the various events that take place in the dynamics, we are interested in following each single trajectory. What I mean is that the previous Lindblad equation can be written in the Krauss form in such a way in which there is a term which describes just the smooth evolution, which is essentially the unitary evolution plus some correction, and eventually some additional Krauss operator, which will correspond to various events which take place randomly in time. Now, if you if you are not able to resolve over all these possible events which takes place due to the interaction, let's say, with surrounding environment, then you end up in considering the dynamics of rho. But if one is able to monitor the dynamics, then actually the state of the system for a given trajectory is described by wave function, the wave function which evolves in a stochastic manner according to this evolution. Say it evolves smoothly, and then at random times it experiences these sudden jumps, or let's say, the sudden jumps, which occurs with a given probability. the interest in following a many-body system at the level of single trajectory is related to a series of recent work starting only 2018, 2019, that pointed out that by looking at quantum circuit, namely evolution plus some measurements, local measurements, it was realized that if you look at the dynamics, keeping a record of the measurement outcome, you get phenomena which are washed out when you look at the average system. What I mean, in this first paper, what was studied was just the evolution of quantum gates plus local measurements done in random positions. Now, if you look at the at the entanglement, then unitary evolution will create some entanglements which, for instance, if you look at half of the system, will grow with linearly with the dimension of the subsystem. On the other side, by doing local measurements, then you tend to favor a separable states. Clearly, if you just measure all the sides, you completely destroy the entanglement. Now, this competition between unitary evolution and local measurement was shown to be responsible for a phase transition in the entanglement between volume law and area law, something which was impossible to see if one is only interested in the average dynamics. And of course, this competition between unitary evolution and measurement actually applies to a more general case in which you have a generic open system which evolves with unitarily plus some local Lindblad, subject to local Lindblad operation. So this picture of, let's say, which was originally designed for, was studied in quantum circuits, in practice applies generically to any many-body open system once you're able to follow the monitor dynamics. And let me specify something important. In the case of entanglement, you have to do it because entanglement is defined, well, in this particular case, given trajectory, the entropy of entanglement is specified once the global state is pure. In general, you may ask if there are phenomena that are invisible to the density matrix, but they are hidden in the monitored dynamics. There is one aspect which is important because this is the motivation of what I'm going to tell you. The dynamics at the level of trajectories is stochastic. So one should consider both a quantum average done on the quantum state and eventually an average over all possible trajectories. Now, this double average will correspond to the trace over the density matrix only for linear observables. If you take any other quantity which is nonlinear in the state, then and the entanglement is one example, then this equality is not there, and that's why there are phenomena which may occur that are not observed at the level of density matrix. Just to give you a picture, because entanglement is not necessarily the crucial ingredient here. So if you look at this stochastic dynamics, which comes over dictated by the evolution over trajectories, then for a given quantity whose average is over trajectories is x, then you can imagine to construct just a probability distribution. Okay? So over this probability distribution, say the average, say the first moment of this probability distribution is what the density matrix will tell you. But of course, the average does not characterize everything, and you may have also interesting or notable phenomena which are present in the higher moments of the distribution itself. In particular, if you look at singularities in the first moment of this distribution, this is what people refer to dissipative phase transition that you see at the level of Lindblad dynamics, but sometimes critical phenomena can occur at the level of higher moments. And when this occurs, then you may have situations that cannot be captured by looking at the density matrix itself. And then you may have very different pictures, that emerge. In the case in which no symmetry breaking takes place, then the average dynamics can be completely featureless, but still, for instance, if you look at entanglement, or I just use entanglement just for simplicity, but if you look at any higher moment, then you may see this transition, for instance, between volume and area law. But in the case in which the system may have by itself symmetry breaking, then several different transitions which occur both in the density matrix and in the higher moment will take place, and those transitions can either coincide or can be distinct. And this depends on the detail of the model that we are considering. There is a problem. So far, out of many theoretical works that appeared, actually there are not so many experiments in measurement-induced transitions. As far as I know, there are 4 or 5 or something. Why? The problem is that, as I said, in order to detect this measurement-induced transition or trajectory-based phenomena, one has to be able to repeat the same trajectory many times in order to build up the average over the quantum state. But then you see that if you have a many-body system, essentially you should be able to reproduce the configuration of jumps in space and time, the same configuration of jumps in space and time many times, But the probability to realize such a situation is exponentially small in the system size or in the time it takes to do the measurement or to reach the steady state. And therefore, it is very hard to really be able to do this few times or many more times, in those times that needed to compute the quantum average. There are a series of works that try to go around these problems, either proposing some feedback dynamics or special types of circuits, or to combine classical analysis and post-processing with quantum dynamics. So our take on this is that we were interested in exploring other cases in which this post-selection barrier can be mitigated, and therefore consider new experimental possibilities to explore trajectories in many-body systems. And I would like to stress, I mean, the discussion here is not only about measurement-induced transition, because in general, while it is experimentally very well established how to monitor single or few qubit system, I mean, there are many phenomena in many-body quantum trajectories besides the measurement-induced transition that can be explored, and having system where this type of monitor dynamics can be done in many-body contexts might be interesting. So we think that if we look at long-range system, this, for various reasons, these post-selection barriers can be mitigated. And in particular, what I will discuss here is infinite range interacting system and their possible implementation in light matter system. So the models that we studied was, so actually the model we studied was Davis-Cummings. So just a cavity with a large spin coupled to the cavity, single cavity modes, and leaky cavity, so where photons can disappear from the system. So if you study the steady-state phase diagram, there are various phases depending on the coupling and the driving, omega. I mean, I guess this phase diagram has been studied several times. I just took it from this paper. And particularly, if you look in this region of the phase diagram, then you can reduce to you just can eliminate adiabatically the cavity modes and reduce it to a spin, to a collective spin decay. So the result I will going to present is in this region, for the full model, I will discuss the entanglement entropy between the spins and the photons, while here I would like to use these simplified models, and I will consider just the entanglement between half of the spin. There is some issues here related to the different unraveling that I think I will not have time to touch, but I will skip. I will be a bit sloppy, but I think it's not relevant here. So the first thing, I just consider this transition, say, between normal and superradiant phase. And this is in the lower part of the phase diagram here, there is just a direct transition, and look at the entropy as a function of the driving. So you see that there is a phase in which the entropy is not essentially dependent on n, and a large driving region in which there is some dependence, like, sorry, the beta should be log to the power beta, log of n to the power beta. It's written strange here. So there is a transition in the entropy. This transition does coincide with a dissipative phase transition that takes place into the system. Something which I would like to stress, that this is accidental, so there is no reason why these two transitions should be coincident, and they do not, let's say, so they coincide essentially, we think, just because we are considering this infinite range model. At finite but long range, this is not the case. We have numerical evidence for that. At the transition, you have just a log divergence of the entropy, while in the superradiant phase, it scales like this power, it becomes this power, this power log to the power beta becomes smaller and smaller, and it looks like you get very, very weak log-log dependence at very large driving frequencies. Situation is different in the larger part of the phase diagram, where there is an intermediate phase, an intermediate bistable phase between, let's say, the normal and the superradiant phase, a bistable phase which essentially has a steady state which depends also on the initial condition. Now, it is a tricky here, because in order to compute the entropy, we should not look at the steady state phase diagram in the way, in this form I presented, which comes from a mean field analysis of the Lindblad, but we have to take the reverse limit. So first we go, we just compute, sorry, I just did it wrong. So we have to do it this way. So I had the chance to do it right, no, 50%, I just put the square on the wrong place. So, okay, I apologize. So the highlight part is the one without the square, let's put it this way. In the phase diagram, you just take first the thermodynamic limit, and then you take t to infinity, but here, in order to compute the entropy, we have to do the other way around, and the two limits do not commute. So indeed, if you see at the bistability, then you see a bistability also in the entropy, which is this greenish parts, and then you see this bistability between a low entanglement and the high entanglement phase. What is interesting is that also in this case, you see a transition in the entanglement. This is the entropy of entanglement between, as I said, in this region is between the photons and the spin, and then you see that here you have a divergence in the derivative. Okay, I'm getting nervous. Okay. And also in this case, the transition is between between an area phase and the sub-volume phase. Again, also in this case, I stress it, is The same singularity occurs in the linear observables. And again, this is a consequence of the fact that we are considering an infinite range system. But what I would like to stress is that we are not interested in looking at the entanglement transition or this monitor measurement-induced transition by looking at the linear observables. We are truly interested in understanding if it's possible to do a measurement of quantities which are nonlinear in the state. So something for which you really need to avoid post-selection barrier. To do this, essentially, what you really need to look is how the probability to have a given trajectory scales with the system size. Now, here, essentially, these models are constructed in such a way that essentially you have a single type of jump. Okay, so for instance, you have photon decay, that's it. So it's a binary sequence. The trajectory is just a binary sequence. So the only thing that you really need to know is what is the minimum length for which this has to be considered. That is, how long does it take for the system to saturate to a steady state? And this saturation time will depend on n. Now, luckily for us, this saturation is typically, for instance, in this region in this lower part of the phase diagram, is logarithmic. This means that instead of having to pay an exponentially large price to get few trajectory, then the overhead just scales polynomially. So, and this is quite some gain in terms of observing trajectory-related phenomena or really be able to monitor the system. The situation is slightly more complicated in the different region of the phase diagram. So this log behavior is not always the case. There are regions in which, especially in this bistable phase, where the divergence is linear. And so this gain, this power law gain, is not there. So given the time I saw from the first thing, I'll skip this and just move in the last few minutes to the experimental implementation. And now here I'm talking about things which, I don't know really about. Okay, so just, okay, so if you have questions, just ask for the first part. Here. So what we like very much about this proposal is that actually experiments can be done using atoms in cavities. And, but there are issues that we are trying currently to understand. So the current experimental situation boils down in having this ratio of the y-axis in the phase diagrams to be around between 2 and 7, while what I've been describing you was at smaller, at smaller values of lambda over k. there are ideas, I mean, by making a bed make it a worse cavity to reduce further this value. The measurement process seems not to be a problem. You just count the photons which comes out from the cavity. There may be an issue related to coarse graining. I mean, photons will come out at different times, so what you can do is just divide the time in bins and then of a certain intervals, and then you decide that the jump occurs in a given bin. So the question that you can ask, so you are going to find what's happening in my family, but because typically when this starts, it's an avalanche process, so because there are cows and nieces, nephews, I mean, so. No, it's too late. It's too late. So I hope there will be no pictures. This is my real world in this now is about pictures. Okay, okay. This is the best way to finish in time, not because of Giovanna, but just to close this. I mean, about this binning. So of course, if this binning is too large, then you lose a sense of the trajectories, and you miss this. But so we just did some additional simulations, and then you see that, well, so as long as you have binnings of the order of 1/k, then things are okay. Then there are other issues which are more subtle, that is, I mean, still the good, I mean, I described about scaling of the saturation time, but prefactors may be too large. So, I mean, we still have to really understand how to push all this to have a nice experimental implementation. That also this saturation time may be leading to some memory-like effect that may be a problem. But the last thing I would like to say that is about these trajectories, things that don't need to be only related to measurement-induced transitions. So, for instance, in this region, I mean, this region is what you may refer also to kind of dissipative time crystals. If you look at trajectories here, they have a very interesting non-trivial behavior, and jumps are highly correlated. So this time crystalline behavior just manifests in the fact that, you know, jumps occur in bursts. And this collective dynamics, which, by the way, might be interesting to design clocks, is, we believe, interesting by itself, not being related to any critical phenomena. And with this, I conclude. So I try to present a model which has both dissipative and measurement-induced transition, which is experimentally motivated. So it's another possibility to implement this many-body trajectory dynamics in a light matter system. It is free in the sense that the overhead that you have to pay is not exponentially large, and in addition, the dynamics of these jumps in a many-body phenomena might be of interest beyond measurement-induced transition. I just flashed this idea about clocks, and with this, I thank you.
Now the session is open for discussion. There are first a question, and then, yes, and then Jamil.
Thanks for a really interesting talk. I wonder how generic this phenomena is in any kind of limit cycle oscillator. So
this last one? No.
The main thing, that the fact that the dissipative phase transition and the entanglement phase transition coincide, right, when kappa is large. So if you have a limit cycle oscillator, you have phase diffusion.
Oh.
If I don't know about that, I have a lot of entropy. If I can monitor the baths, well, I know what the phase is doing. I'll have strong correlation. Like, is that enough, you think? Because that would tell you these things coincide.
So
right?
what I think is the reason of this coincidence is not related to this oscillation, rather to the fact that you have an infinite range system. If you study a long range system, you already see that the two transitions split. Because you see, the dissipative transition requires that the spins are correlated. And they will be correlated both by quantum and classical fluctuations. And what happens is that typically the dissipative transition is more robust to the environment rather than this entanglement.
Yeah, but in the fully collective limit.
In the fully collective...
It becomes almost like just the physics of a simpler limit.
Yeah, exactly.
So can I get the same physics in like a single bosonic mode that has limit cycle physics, and I would see like correlations between the output light and what the mode is doing, and that would be entanglement too? I'm curious if there's something qualitatively different, yeah.
I don't know. Yeah, I would tend to agree, but I'm not that sure.
Okay,
yeah.
Cool, thanks.
Hi, Sal. It's great to have you here. So perhaps it is related somehow to what Ash was asking. I wonder how much you are somehow surprised by the result, right? Because the decay model or all these collective spin models predicted by light, a large end, they're going to have weak correlations. So cumulants are good to describe them. We also know that at a critical point there will be more entanglement. It's the paper by Alessio and Silvia, right, that you get a lot of squeezing when you quench a criticality. So the fact that you get a very weak post-selection barrier for this type of models, perhaps you could have anticipated, and perhaps, but you tell me if I'm getting it wrong, doesn't solve the issue of hybrid circuits where there are extended systems.
I totally agree. So I don't want to present this as a big surprise.
Okay.
I'm just saying it's an avenue that we think is interesting to explore. But there is nothing mysterious, I would say.
Okay, so you would have expected the outcome before.
Not that I'm coming and say, okay, this should be exponentially hard, and then I show you that it's not. No, I'm just saying, look, I think these are interesting system where to study quantum trajectories. Let's put it this way.
Okay.
But given the fact that there are not so many experiments around, I think it's that you have additional places where to look at these trajectories in many body contexts.
Can you comment on the order of limit problem which you referred to, that first you have to take the steady state and only then the thermodynamic limit?
Yes, because the mean field is obtained by just taking the limit n to infinity, and then you can look at the steady state diagram. But if you want to know the entanglement, then you have to make a partition. So you cannot take the limit n to infinity first. So what you have to do is first you define the partition and take the steady state. So you take the limit t to infinity, and then eventually you want to see the scaling, meaning you take n to infinity.
So So you had mentioned on one of your slides that there has to be some underlying semi-classical picture. So I thought that actually you have to do some kind of mean.
No, we don't use, I did not comment on that, but I can add. What we saw is that in general, if you take, so let me finish first, and these two limits do not commute. So when I consider the entropy, I have a given prescription that will not lead to the same thing on the other way. Now, so here I presented the case of infinite range, but we have that, let's say, we study also long-range systems, and also for various different reasons, or in general, in long-range system, then you also have ways to avoid this post-selection. And we think that this is somewhat related to the fact that you have an underlying semi-classical dynamics, and you have weak fluctuation around this classical state, which is probably what Jamir was mentioning.
Thanks.
And actually, again, it's also related to, it's the same thing, because you boils down with a squeezed state of bosonic modes. Yes, yes.
So I have a question on the collective jumps you were showing.
Mm-hmm.
And first of all, how can you say they are collective? And have you analyzed the spectral properties? So
yes.
How the waiting time distribution behaves?
So they are collective because they don't, so you see that, okay, sorry. They occur in bursts. This is again okay, here. So you see that this is, for instance, the number of jumps as a function of time. Now, if they were kind of independent, then you would just see just a straight line. Okay? So the number of jumps just increases linearly. But actually, this is not the case. It increases in steps. So there are particular regions in the dynamics where you have many jumps, and then the system gets quiet, and for some time there is no jump. This is essentially the trajectory dynamics related to the limit cycle.
So
nothing else.
Can I see a feature that is associated with the number of particles?
So, yes. Here, if I manage. So if you look at the waiting time distribution, then you see that this waiting time distribution, so between two jumps, becomes sharper and sharper if you increase the number of particles. This is again kind of collective effect, okay? That's why we would like to understand how this can be used for clocks.
So if there are no further questions, we thank Saro again.